everyone, my name is Stanislav and today I will talk about our paper called AttrLostGAN, Attribute Controlled Image Synthesis from Reconfigurable Layout and Style. My co-authors are Avneesh, Sharma, Joern, Hees, Tushar, Karayil, Federico, Raue and Andreas, Dengel. So just a quick personal introduction. I'm a third-year PhD student. I joined the University of Kaiserslautern and the German Research Center for AI in 2019. I am supervised by Professor Andreas Dengel, and my interests are controlled image synthesis, representation learning, but also vision and language systems in general. So what makes a good image synthesis model? So for once, we want images to be realistic and diverse. But also, if we are providing input labels, such as classes or attributes, we want the generated images to reflect them. Another one is control. We want to give the users intuitive knobs to change the image to create what they have in mind. And the focus of our work is this control aspect. So in 2019, there was a work called LostGAN, which is a method for diverse image generation from layout. So it works by providing individual noise vectors for all the bounding boxes in a layout. So each bounding box has a corresponding label, but also a separate latent code sampled from a Gaussian distribution. And this design allows us to generate multiple diverse images from the same layout. Now you can also reconfigure bounding boxes and class labels, such as shown on the right-hand side, where we move the bounding box a little bit to the left, but we keep the appearance more or less the same since we don't change the latent codes. So one problem in this method is that it doesn't have control over the specific appearance. While we can sample different latent codes for the bounding box, until we are happy with the result, we cannot specify, for example, a particular color for the jacket of this person. So in our method, we use optional attributes for the bounding boxes. So not just the class label, but also attributes which can specify all kinds of different things. So here, for example, we start with a cloudy sky and grass. Now we can add a tree, which is green. We can add a plane that's metal and orange. We can also add a sheep that's white, a horse that's brown, a person, and then specify that this person should have a jacket that is pink. And one also very cool aspect of our work is that you can go back to the bounding boxes that you have generated previously and, for example, add this attribute dry to grass. And you can see that all the other parts in the generated image stay the same. So let's come to our method. We have a generator that takes as input a Gaussian noise for the full image, pass it through a linear layer, and then a couple of rest blocks to produce a generated image. And in terms of conditions, we have bounding boxes, labels, and attributes. Now we embed the labels as well as the attributes by passing them through an MLP. We concatenate the label embedding, attribute embedding, and the latent codes for each of the bounding boxes, and use this intermediate vector to predict masks for the individual objects and also project them to compute gamma beta parameters to modulate the features in the rest blocks. So essentially this normalization method works like batch norm. We first normalize the feature maps as in batch norm, but then we recalibrate as in adaptive instance normalization, which you know from StyleGAN, but we condition it on the layout. So we don't calibrate it. We don't calibrate all spatial locations with the same gamma beta parameters, but we recalibrate it based on the location and based on the embedding for that location. Now the discriminator just is a standard CNN composed of different rest blocks, and at the end we have two separate head networks to compute 3 different scores. The image head computes a score for the realness of the full image, and the object head computes 2 scores for the realness of the labels and the attributes separately. So here you can see some qualitative results on a synthetic dataset which we created for Dialog from Dialog Amnest. We have 10 digits, and as attributes there is digit colors, background colors, and styles. And here we have shown that our method works on this simple dataset. We can change the background color, the digit color, and the digit labeled without affecting anything else in the generated image. We can also move a bounding box without changing stuff. However, there is a failure case, which might not really be a failure case in complex images, is when objects start to overlap. Then because of the location, the features are modulated by both parts, which can be useful to modulate interactions between objects. But in this particular case, it looks like a failure example because we cannot really recognize the 5 and the 2 anymore. Now let's come to the qualitative results on Visual Genome. We have over 178 categories and optionally multiple attributes from a set of 80. So on the top you can see the layout, and in the bottom you can see real images. The second row shows the only other baseline that considers attribute-controlled image generation, and in the third row our method. So in general we can see that our method much better reflects the input conditions and is visually much more similar than the real images, but individual objects are still very hard to recognize. So let's come to the quantitative results. We use multiple metrics to measure object quality, but also class fidelity as well as attribute fidelity. So here is the baseline that we use to compare our method with. And our method, first of all, produces images that are much better globally in terms of inception score and FID. In terms of object class quality, we reach a similar performance without auxiliary classification losses. And we have a much better result on the attribute fidelity. So as limitations, our method is still far from generating realistic complex images, and we require attribute annotations. We have open sourced our code, where you can also find a Jupyter notebook with a demo. So let's conclude this talk. We presented a new method for attribute-controlled image generation. We evaluated our method on a toy dataset as a proof of concept, and then evaluated it on a realistic dataset. We have better performance across different metrics. We provide users with intuitive control, and for next steps, we focus on enhancing image quality as well as resolution, figure out if we can produce similar results in an unsupervised way without requiring attribute annotations, and whether it's possible or not to turn the fixed set of labels and attributes into freeform text descriptions. And with that, I would like to say thank you